Hey folks, my name is Karamcheti, and I'm a second year PhD student at Stanford. I'm really excited to be here at ACL presenting some work on active learning for visual question answering with my amazing mentors Ranjay Krishna, Fei-Fei and Chris Manning. Specifically, I want to talk about a negative result, that most of the modern active learning toolkit fails to see gains in sample efficiency on VQA. I think the best way to tell the story of this project is from the beginning, starting from our initial goal. How do we build VQA systems that grow and adapt via interaction? As a starting point, I like to think of modern VQA models in terms of the capabilities they present. For example, given a question like what is the woman to the right of the boat holding, the corresponding answer is an umbrella. The capabilities to answer this question involve reasoning over referring expressions and simple object recognition. Similarly, given a question like is the umbrella upside down, the corresponding answer is yes. The capabilities here are again object recognition, but also a little bit of common sense reasoning. Thinking broadly in terms of capabilities was an abstraction we made early on to qualify what sorts of questions VQA models were good at answering. We took this a step further and asked, can we augment the capabilities of VQA systems by leveraging humans in the loop? Specifically, let's say we do the following. First, starting with a pre-trained VQA model, let's allow a bunch of users to ask the model some questions and have them flag which questions the model failed to answer and which ones they answered easily. Then let's show the results of this to another set of users who try to find patterns by looking at these questions. By doing so, they curate examples to add to a capability dataset that enriches a VQA model along a targeted axis. For example, getting better at the emotion recognition questions shown here. The hope is that by retraining on this dataset, we can learn this new capability. And if we continuously redeploy the system with this collection process, we can continually grow our system. Running all these experiments directly with crowd workers from the jump would have been hard. Getting the models and the interface right would have taken time, and more importantly, it would have taken a lot of money to run at scale. So we decided on a simple sanity check. If we ran active learning, simulating part of the process I just described, how do we do? Specifically, we wanted to answer the following two questions. One, can we identify useful examples to label and add to our dataset? And basically, would a human be able to flag the right types of questions? And two, can we actually meaningfully learn from these examples to grow our capabilities? A quick recap of active learning in our context. Given a VQA model trained on some amount of data, say 40,000 examples, or roughly 10% the size of the VQA2 dataset, iteratively acquire batches of unlabeled examples from a larger unlabeled pool. There are tons of possible acquisition strategies. If you check out our work, we look at around 8 in total. The simplest baseline that you should beat, however, is random acquisition. How well do you do if you pick data from this pool at random? Beyond that, the big divide is between methods that look at model uncertainty. For example, what's the maximum confidence I place on any answer when predicting for an unlabeled example, versus example diversity. How different is this new example from things we've already seen? We look at both of these in our work. And specifically, when we run some of these methods out on VQA2 out of the box, we're a little surprised. Concretely, this graph shows performance when training a bottom-up, top-down attention model for VQA on 10% of the VQA2 dataset, then performing active learning by adding batches of 40,000 examples at each iteration. We test this with two uncertainty-based approaches, least confidence and BALD, Bayesian active learning by disagreement, and one diversity-based approach, core sets. And in gray, beating all the other fancy active learning strategies is a random acquisition baseline. In other words, active learning for VQA does not seem to work. And this is where the project took a turn, and this is what I'll be spending the rest of the talk diving into. Why not? Before getting started, I have to acknowledge the great work that we build on. Our starting point was work by Lin and Parekh that looks at active learning with deep VQA models on the initial VQA dataset. Their key punchline is that active learning doesn't really work for VQA unless you start with a ton of labeled examples, almost a majority of the original dataset. In a similar vein, though not related to VQA, Siddharth and Lipton performed a large-scale study of various active learning methods on binary classification tasks in NLP. While they identify Bayesian active learning, or BALD, as a solid strategy, there's a general trend in their results about how the delta between active learning and random baselines is rather small. This is followed up by work by Lowell et al. That start to analyze the value of active learning and NLP altogether, showing that the results of active learning models don't quite hold up across models or different tasks. In general, our work is complementary to all of this. We also notice that active learning performance doesn't hold up across models or tasks. But the key difference in our work is that the analysis that we perform, we try to isolate exactly what in these data sets is holding active learning back. And so let's dive into these curiosities, our large-scale study trying to understand why active learning doesn't work for VQA. The first question we had was whether the results we were seeing generalize across models and across active learning functions. There are several VQA models out there, ranging from simple LSTM CNN-based fusion models to more bespoke attention models like the bottom-up, top-down attention model pictured on the left. There are also more complex models that pre-train on large amounts of text and image data like LexMERT, which you can think of as a multimodal extension of BERT. However, we found the same story here. Regardless of the model type, including simpler models, we still see an inability for active learning methods to be more sample efficient than random baselines. So then we look to other active learning acquisition strategies. So far, I've shown you the results of uncertainty sampling and BALD, but we also try other methods, including a variant of entropy-based uncertainty sampling, as well as by looking at the entropy of a Monte Carlo dropout ensemble, as well as two other variants of core sets that look at unimodal representations of language and vision separately. We still see the same story. So if it's not the models or the strategies, what is it? Well, the next place we looked was the data. Maybe this is just a VQA2 problem. However, when we look at other standard VQA datasets like GQA, we see a similar story. This is especially interesting given that GQA is synthetically constructed. And yet, for whatever reason, active learning fails to work. We even tried simplifying the problem and created a version of VQA2 with questions only having to do with sports, basically turning VQA2 into a 20-class classification problem. While we're able to get higher absolute validation performance, relative sample efficiency gains for active learning still aren't there. This holds across other models and acquisition strategies as well. So what's going on? If these quantitative metrics aren't telling us anything, what about something more qualitative? To complement these coarse aggregate studies, what if we actually took a look at the examples being acquired by these algorithms? This was the turning point. After training a bottom-up model, we ran out least confidence uncertainty sampling and just dumped examples that it returned. Looking at them in mass, we started to see a pattern. In order, we have a question that requires a pretty sophisticated amount of external knowledge to answer, a question that requires the ability to recognize words and run OCR in a snippet of an image, and a question that is so underspecified, I don't think I could guess the right answer if I tried. In other words, we found that active learning was returning what we called the collective outliers of a dataset. Groups or subsets of examples that are semantically similar, presenting as just beyond the ability of existing models, questions they just can't answer. And if this is the hypothesis, how do we, one, quantify these examples, and two, test this out? In terms of quantifying these examples, it was around this point of the project that the EMNLP 2020 papers were being dropped left and right. One idea in particular stood out as being very useful for our work. Dataset maps, introduced in the dataset cartography paper by Sovaswayam Dipta and folks at UW and AI2. Constructing a dataset map is really simple. Here's one for the bottom-up attention model trained on VQA2. Conditioned on a model that you're training in a given dataset, track the confidence assigned to given examples across training epochs. At the end of training your model, plot each example from your dataset on a graph where the y-axis is the average confidence assigned across epochs, and the x-axis is the average variability, the spread of those values. You then color each point on a spectrum based on the average correctness assigned across epochs. I highly recommend you check out the original paper for more detail. But the real beauty of these dataset maps is that they intuitively paint a picture of the difficulty of an example, what's learnable and what's not. Examples near the top of the map are super easy to learn. However, as you climb down the map, especially towards the bottom left, you start to run into harder and harder examples, bottoming out at examples that are assigned zero confidence, examples that the model never places probability mass on the right answer for, with zero variance. Given these maps as a backdrop, it becomes really easy to get a picture of what active learning is doing. Coloring each acquisition over time by its position on the dataset map, we see that the random baseline returns examples proportional to their presence in the map, as we expect. But looking at active learning strategies, we see something else. Core set starts picking the medium-hard examples, then proceeds to pick the harder examples until it rebalances towards the end. BALD, the strategy that performed so well in prior work, is actually even worse. It picks the hardest examples from the jump, then continues to pick them until they've been exhausted from the data set. And least confidence uncertainty sampling follows a similar trend. In other words, what we saw qualitatively has been confirmed. Active learning is picking these collective outliers, these hard or impossible to learn examples. And they're picking them early on in acquisition, impacting learning, and then further spiraling as we acquire more and more data. But this begs the question, what happens to active learning performance as we remove these unlearnable collective outliers? If there's any slide to pay attention to in this talk, it's this one. Let's start by removing examples based on their position in the original dataset map, just moving up the y-axis based on confidence. Just looking at the post-hoc dataset map, identifying and removing all the hard examples. If we remove 10% of the dataset in this fashion, we don't really move the needle, and that's fine. Recalling the original map, there are a lot of these really hard examples. But as we remove 25 to 50% of the dataset, this starts to tell a completely different story. At 50% of the most difficult examples in the dataset removed, all of the active learning strategies, the two pictured as well as all the others, start to have significant gains in sample efficiency over the random baseline. In other words, it really does seem that these examples, these collective outliers, are really part of the problem that's holding active learning back from performing so well on these open-ended tasks. And that's where today's story ends. We started with an observation that active learning doesn't work for VQA. We then diagnosed the problem through a pretty large-scale study testing several active learning strategies. And then finally, through use of dataset maps, we teased out a possible cause and verified it with a systematic ablation. And it comes full circle. These collective outliers are just the very same capabilities I mentioned when motivating this project. Hard common sense questions or questions dealing with underspecification or OCR and so on. Until we can figure out a language and a formalism to think about these phenomena when building VQA models, or arbitrary models for such open-ended tasks, I fear that this is going to remain a problem for any work in active learning. So what's next? Despite this negative result, we have a lead. And that lead is that if we could build models that could ignore these unanswerable questions, say, I don't know in the presence of these new collective outliers, these new capabilities, we could build better active learning systems that are more robust and more performant, and build more reliable machine learning systems as a whole. Thank you all so much. I'm looking forward to seeing you all and talking to you at the rest of the conference. Cheers.